Number 32 is a synthesis problem that requires you to use some old reactions from the second exam. So let's start by looking at what's the same and what's different. Well, we still have a 5-member ring between the two answers, and this carbonyl is untouched. All that changed is somehow we got this ester group to become 2 more carbons that are attached by a double bond. So the only reaction that I can think of that involves the formation of carbon-carbon double bonds, where you once had C double bond O, is the Wittig reaction, meaning the reaction where you see that PPH3 and double bonded to the phosphorus is whatever carbon chain you want to add. So I'm looking to add probably 2 carbons, because if this is carbon 1 and this is carbon 2, this is probably carbon 1 and carbon 2 over here. But now remember, the Wittig reagent only reacts with C double bond O, not ester C double bond O. So I need to turn this into a regular carbonyl, not an ester carbonyl. Now also realize that since this reacts with carbonyls, it may want to react with this. So this is a general rule of thumb. When you're doing a synthesis problem and you see that a carbonyl is virtually unchanged between reactant and product, it's probably a good idea to protect it. Because if you protect it, it can't react with anything. Also, for the reason I said before, if I want to react with the Wittig reagent here, but not here, I probably want this to be protected. So your first step of this synthesis should be to add a protecting group. And your go-to protecting group from the second exam was your acetyl protecting group, your diol, which makes orgobeast. So what all you have to do is redraw the structure exactly the same. I'm going to give myself a little more room. Redraw your structure exactly the same. Now draw your diol next to the carbonyl's oxygen, like a little hat. Now erase that double bond O, erase the hydrogens, and connect the 2 oxygens from the OHs to the carbon where the double bond O used to be. And so there's your orgobeast, and your carbonyl is now protected. All we have to do to get it back is use H3O positive. So now, why did this carbonyl get protected but not this carbonyl? Because the orgobeast, the acetyl protecting group, only reacts with ketones and aldehydes. It doesn't react with carboxylic acids or esters or any other kind of carboxylic acid derivative. So that's why this doesn't react, but this does. And now I'm free to turn this into just a regular old carbonyl. And there's a really easy way of doing that. You could, all you have to do is react this with dival H. Because dival H is that special reducing agent that turns carboxylic acid derivatives into an aldehyde. Meaning I would get, after using dival H, I would get this regular old aldehyde. So I'm sure that's not cut off. Okay, good. Now I have that aldehyde, and I'm free to do the Wittig reaction. So I can use that. I want to add 3 and 4. So I'm going to write PH3, P, and then double bonded to that should be carbon 3, and then carbon 4. And that will take me to this, but the orgobeast would still be there, so I also have to remove that. And how do you remove orgobeast? You use H3O positive. So technically what I would have at this point is this, but then just using some H3O positive will bring me home to finish the synthesis, and I will get what my intended product was. So now looking at this question, are there any other modifications, any other ways of solving this problem? Well, I think the Wittig reaction was very intended to be your only way of getting this double bond here. There are other ways you could do it using Orgo-1 reactions, but I honestly think you should be very familiar with the Wittig reagent, so I think it's better to practice with this than trying to work your way around it, because even if it's not a synthesis problem, you're definitely going to have to use the Wittig at some point on your final. But as far as going from this to this, how can other ways we can get the carbonyl? Well, you could have used OH minus, which would have converted this ester into a carboxylic acid, and then you could reduce that carboxylic acid and then oxidize it to a carbonyl, but that's a bunch of extra steps. Why not just use dival-H, because it'll do that in one step. But if you want to see those things that I'm talking about, that I kind of just mumbled to myself about, first you would do OH minus, and then H plus, step 2. Because what that does is it turns an ester into a carboxylic acid, so I have this. Then I could reduce that carboxylic acid using LiAlH4, and that would convert this into a alcohol. So it would look like this. And then I can oxidize that alcohol into the carbonyl I wanted using PCC. And so that would turn into that. But that's 3 steps where you could have just done this in one with dival-H. And as far as protecting groups are concerned, in this semester, really the only protecting group you can use is the acetal protecting group, which we kind of pretended that the OTB-DMS that we taught you from last semester has disappeared off the face of the planet. But that's the general gist behind this synthesis. The key points I want you to take away is, 1, when do you use a protecting group in a synthesis? Well, there are 2 reasons. I didn't actually turn this back into a carbon. Oops. There are 2 reasons where you would want to use a protecting group. Where you see that in the reactant and the product, a carbonyl is unchanged. That's probably your first hint. The other would be in a reaction where you see there are 2 separate carbonyls, but you only want to really mess around with one and save the other for later. So maybe there's a reaction where I do want to use this carbonyl, but not until after I finish with the ester. In that case, you need to protect one while you can't protect the other. And that's the general gist of it. Make sure you know the Wittig reagent, though. That's a very important reactant to have a good grasp on for the final.